A violent pulse of energy surged through the Pacific coastline of southern Mexico, sending waves of shaking across hundreds of miles, and reminding millions that one of Earth's most powerful geological engines never truly rests. Offshore from Puerto Madero, where the deep waters of the Pacific conceal one of the planet's most active tectonic boundaries, a magnitude 7.3 earthquake erupted with astonishing force. Within moments, coastal communities were rattled awake, buildings swayed far inland, and seismic instruments across the globe registered another major release of energy from the restless Middle America Trench. The earthquake struck on the 17th of July, 2026, at approximately 14 minutes before 3 in the afternoon, Coordinated Universal Time. Its epicenter lay roughly 58 miles, or about 93 kilometers, west-southwest of Puerto Madero, at a depth of approximately 11.5 miles, or 18.6 kilometers. Although that depth may appear significant on paper, in geological terms it was remarkably shallow, allowing the released energy to travel efficiently toward the surface. Residents across southern Mexico described long, rolling motions followed by powerful jolts that seemed to continue far longer than expected. Within little more than half an hour, the Earth delivered another reminder that major earthquakes rarely arrive alone. A magnitude 6.0 aftershock struck roughly 56 miles, or about 90 kilometers, southwest of Puerto Madero at a depth of approximately 6 miles, or 10 kilometers. Less than 24 hours later, another powerful aftershock measuring magnitude 5.7 shook nearly the same offshore region. By then, scientists had already cataloged dozens of earthquakes exceeding magnitude 5 and a growing sequence of more than 46 aftershocks, transforming the rupture zone into one of the most closely monitored seismic regions anywhere on the planet. Yet for many people watching events unfold from thousands of miles away, another question quickly began dominating conversations. If a powerful earthquake has ruptured beneath the Pacific off Mexico, does the released energy pose any danger to California? Social media rapidly filled with speculation. Old theories resurfaced claiming that one major earthquake automatically triggers another along distant faults. Some suggested the San Andreas fault might somehow awaken next. Others wondered whether seismic waves traveling through Earth's crust might destabilize faults across western North America. Those concerns are understandable. Earthquakes possess a unique ability to capture public imagination because they strike without warning and because their effects often appear connected across vast regions. However, the scientific reality is considerably more complex, and understanding that reality begins deep beneath the Pacific Ocean. Off the southern coast of Mexico lies one of the world's classic subduction zones. Here, the oceanic Cocos Plate relentlessly moves northeastward toward the North American Plate at a speed of approximately 3 inches every year, or roughly 76 millimeters annually. That motion may seem almost imperceptible compared with everyday human experience, yet over decades and centuries it stores extraordinary amounts of stress within the rocks where the two tectonic plates meet. Unlike faults that slide horizontally past one another, a subduction zone involves one tectonic plate diving beneath another into Earth's mantle. As the heavier oceanic crust descends, enormous friction prevents smooth movement along sections of the plate boundary. Instead, those sections become locked together. Year after year, the moving plate continues attempting to advance while the locked interface stubbornly resists. The rocks gradually bend, compress, and accumulate strain, much like an immense spring being wound tighter with every passing year. Eventually, that strain exceeds the strength of the rocks. When failure finally occurs, the stored energy escapes almost instantaneously. Huge portions of the fault can lurch several feet, or well over 1 meter, within seconds. That sudden movement displaces enormous volumes of rock, launching powerful seismic waves in every direction. Depending on the amount of vertical movement along the seafloor, the same process can also disturb vast quantities of seawater and generate tsunamis capable of crossing entire ocean basins. The focal mechanism calculated for the 17th of July earthquake clearly indicates reverse faulting, commonly known as thrust faulting. That pattern matches precisely what geologists expect from movement along the subduction interface between the descending Cocos Plate and the overriding North American plate. Rather than sliding sideways, one block was forced upward relative to the other, releasing centuries of accumulated tectonic stress. Although the earthquake surprised many observers because of its magnitude, the region itself has repeatedly demonstrated its capacity for producing destructive seismic events. Historical records reveal an extraordinary pattern extending back decades. Since the middle of the 20th century, at least 50 earthquakes measuring magnitude 7 or larger have ruptured sections of the active plate boundary extending through Central America. That statistic alone illustrates the relentless pace at which tectonic forces reshape this portion of the Pacific margin. Even more striking is the concentration of major earthquakes surrounding the latest rupture. Within approximately 155 miles, or 250 kilometers, of the current epicenter, at least 7 earthquakes exceeding magnitude 7 have occurred since the year 1950. The latest rupture, therefore, did not emerge from an unexpected location. Instead, it struck within one of Earth's most consistently active seismic corridors. Its position also overlaps with several historically significant events. In 1970, another magnitude 7.3 earthquake ruptured a nearby section of the same subduction boundary. More than 2 decades later, during 1993, a magnitude 7.2 earthquake again shook much of the region. That event produced severe damage extending into Guatemala and claimed at least 1 life, despite occurring offshore. Perhaps the most striking comparison comes from the devastating magnitude 8.2 earthquake that struck during 2017. Although that earthquake involved a different style of faulting within the descending Cocos Plate, rather than directly along the plate interface, its rupture extended close to the northern edge of the latest event. The 2 earthquakes, therefore, occupy neighboring segments of an exceptionally active tectonic environment that continues adjusting under immense geological forces. The 2017 disaster demonstrated the destructive potential of southern Mexico's offshore faults. Violent shaking affected multiple states, infrastructure suffered extensive damage, and approximately 20 people lost their lives. The earthquake also generated a regional tsunami, providing a sobering reminder that subduction zones can threaten both land and sea simultaneously. Against that historical backdrop, scientists immediately began examining whether warning signs had preceded the latest rupture. Interestingly, the answer appears to be yes. Several days before the main shock, on the 14th of July, seismic instruments recorded a relatively modest magnitude 4.1 earthquake near the eventual rupture zone. Such events occur frequently along active plate boundaries and usually attract little public attention. Then, approximately 88 minutes before the magnitude 7.3 earthquake, another foreshock measuring magnitude 4.7 struck remarkably close to where the main rupture would begin. Only in hindsight do these smaller earthquakes reveal their significance. Foreshocks remain one of the most fascinating yet frustrating aspects of earthquake science. They cannot reliably predict when or whether a larger earthquake will occur because the overwhelming majority of moderate earthquakes never lead to major ruptures. Only after a devastating main shock has already happened do scientists identify which earlier earthquakes were genuine foreshocks rather than ordinary background seismicity. That limitation highlights one of the greatest challenges facing modern seismology. Despite remarkable advances in satellite observations, high-resolution global positioning system measurements, artificial intelligence, machine learning, and dense seismic monitoring networks, no scientific method currently exists that can predict the exact time, place, and magnitude of a major earthquake before it begins. Researchers can identify hazardous regions, estimate long-term probabilities, and monitor changing stress patterns, but the precise instant when accumulated strain finally overcomes friction remains beyond current forecasting capabilities. As aftershocks continued rippling through the offshore rupture zone, specialists turned their attention toward mapping the evolving fracture beneath the Pacific seabed. Every aftershock serves as another clue, outlining portions of the fault that slipped while identifying neighboring sections that may still be adjusting. Instead of viewing aftershocks merely as isolated events, Geophysicists examine them collectively as a living blueprint of the earthquake itself, revealing the hidden geometry of the rupture thousands of feet beneath the ocean floor. Far beyond Mexico, however, another concern refused to fade. Thousands of miles north along the Pacific coast, attention increasingly focused on California, where memories of historic earthquakes remain deeply woven into public consciousness. With one major tectonic system having just unleashed enormous energy, many wondered whether another famous fault system might somehow be next. Even as aftershocks continued to ripple beneath the Pacific Ocean, discussion increasingly shifted from what had already happened to what might follow. California inevitably entered that conversation. Headlines, online posts, and hurried speculation began drawing lines across maps of the Pacific, suggesting that a powerful earthquake off southern Mexico might somehow be the opening move in a much larger sequence stretching northward along the western coast of North America. It is an idea that resurfaces after almost every major earthquake around the Pacific Rim, fueled by the simple observation that these regions all occupy the edge of the same immense ocean. Yet the geological reality is far more intricate than the appearance of a continuous coastline. The Pacific Ocean is surrounded by what geologists commonly describe as the Ring of Fire, a sweeping belt of volcanoes, deep ocean trenches, and active faults extending for roughly 25,000 miles, or about 40,000 kilometers. This immense geological boundary wraps around the Pacific Basin like an enormous horseshoe, connecting the tectonic margins of New Zealand, Indonesia, Japan, Russia, Alaska, Canada, the United States, Mexico, Central America, and South America. Nearly 3/4 of the world's active volcanoes and the overwhelming majority of the planet's largest earthquakes occur somewhere along this restless perimeter. Despite that connection, the Ring of Fire is not a single fault capable of rupturing from one nation to another like a crack racing through a sheet of glass. Instead, it consists of dozens of separate tectonic plates interacting in different ways. Some collide, others pull apart, many slide sideways. Every boundary possesses its own geological character, stress history, and rate of movement. What occurs in one section does not automatically dictate what happens elsewhere. The earthquake offshore southern Mexico originated within the Middle America Trench, where the Cocos Plate descends beneath the North American Plate. California, by contrast, is dominated by an entirely different tectonic environment. Much of the state's famous seismic activity is controlled by the San Andreas Fault System, where the Pacific Plate and the North American Plate grind horizontally past one another in what geologists call a transform boundary. That distinction is far more important than it may initially appear. In southern Mexico, the principal motion involves compression. One plate dives beneath another, storing energy through immense squeezing forces until the rocks finally rupture in thrust faulting. Along much of California, however, the dominant motion involves lateral movement. Instead of one plate plunging beneath the other, the two plates slide sideways, accumulating stress in a completely different manner. Although both environments produce destructive earthquakes, they operate according to different mechanical processes. That difference alone makes a direct cause and effect relationship between the Mexican earthquake and California considerably less likely. This does not mean distant earthquakes have no influence whatsoever. Every large earthquake launches seismic waves that race through Earth's interior at extraordinary speeds. Some waves travel several miles every second, passing beneath continents and oceans alike before gradually dissipating. Sensitive instruments detect these waves circling the planet multiple times after the largest earthquakes ever recorded. Scientists have long recognized that these traveling waves can temporarily disturb faults located thousands of miles away. The key word, however, is temporarily. Dynamic stress changes caused by passing seismic waves may trigger tiny earthquakes or brief bursts of seismic activity on faults that were already extremely close to failure. Such triggering has been documented following several of the world's greatest earthquakes. In some cases, geothermal regions experienced increased activity. Certain volcanic systems displayed subtle changes. Small earthquake swarms occasionally appeared far from the original rupture. Yet there is an equally important observation. Those distant responses almost always involve relatively small earthquakes rather than catastrophic failures of major fault systems. Decades of global research have failed to establish convincing evidence that a major earthquake in one tectonic setting reliably triggers another major earthquake thousands of miles away on an entirely separate plate boundary. Earth's crust simply does not behave like a perfectly connected chain of falling dominoes. One of the strongest examples often cited emerged after the colossal magnitude 9.1 Sumatra Andaman earthquake during 2004. That earthquake generated devastating tsunamis across the Indian Ocean and released one of the greatest amounts of seismic energy ever measured by modern instruments. Seismic waves from the event traveled around the globe, and researchers observed increases in tiny earthquakes within geothermal regions as far away as Yellowstone National Park in the United States. Those Yellowstone earthquakes attracted enormous public attention. Some interpreted them as evidence that a supervolcano had awakened. Scientific analysis painted a much calmer picture. Researchers determined that the passing seismic waves temporarily altered pressures within Yellowstone's hydrothermal system, encouraging numerous small earthquakes that remained well within normal background activity. No eruption followed. No catastrophic escalation occurred. Instead, the observations provided valuable insight into how dynamic stresses interact with faults already under natural tension. The lesson proved remarkably important. Large earthquakes can influence distant regions, but influence is not the same as imminent disaster. The same conclusion emerged following the magnitude 9 earthquake that struck Japan during 2011. Sensitive monitoring detected temporary changes in seismic activity across various parts of the world, yet no evidence suggested that distant major faults suddenly became destined to rupture simply because the Japanese earthquake had occurred. California itself provides another useful example. The San Andreas Fault extends for approximately 800 miles, or about 1,300 kilometers, through the state. Yet even along this single fault system, stress is not distributed evenly. Different segments possess different histories, different geometries, different frictional properties, and different rates of accumulated strain. Some portions rupture relatively frequently. Others remain locked for centuries before releasing enormous amounts of energy. This uneven distribution explains why forecasting remains extraordinarily challenging. Scientists know certain sections of the San Andreas are capable of producing earthquakes approaching magnitude 8. They also understand that parts of Southern California have not experienced a rupture comparable to the Great Fort Tejon earthquake of 1857 for well over a century and a half. That long interval naturally attracts scientific attention because tectonic plates have continued moving throughout all those years. The Pacific plate has not paused, neither has the North American plate. Every passing year adds a little more strain where the fault remains locked. Yet strain accumulation alone cannot reveal precisely when failure will occur. Imagine slowly bending a thick steel bar. It resists for a long time, storing energy internally while showing surprisingly little outward change. Eventually it snaps, but predicting the exact second of failure proves almost impossible because microscopic variations inside the material govern the final moment. Faults behave similarly, except that the materials involved are fractured rocks extending for hundreds of miles beneath Earth's surface. That complexity is why seismologists avoid making deterministic statements after distant earthquakes. Instead, they rely upon statistical analysis. Following major earthquakes, agencies around the world examine whether stress transfer calculations indicate elevated hazards on nearby faults. These calculations are most meaningful close to the rupture itself, generally within tens rather than thousands of miles. In the case of the Mexican earthquake, the greatest concern naturally centers on neighboring sections of the Middle America Trench and nearby crustal faults capable of producing significant aftershocks. Indeed, aftershocks remain the most immediate hazard facing affected communities. The sequence following the magnitude 7.3 earthquake demonstrates precisely why. Within minutes, the magnitude 6.0 aftershock struck offshore, proving that substantial portions of the fault continued adjusting after the initial rupture. Then came the magnitude 5.7 event, followed by dozens of earthquakes exceeding magnitude 5. Every one of those aftershocks represented additional movement as the crust sought a new mechanical equilibrium. Contrary to popular belief, aftershocks do not occur because the Earth is getting rid of leftover energy. Instead, the main shock dramatically changes stress across the surrounding fault network. Some areas experience reduced stress because they have already slipped. Others receive additional stress, pushing neighboring patches closer to failure. Those newly stressed areas then rupture in turn, producing aftershocks that gradually decrease in both frequency and magnitude over weeks, months, and sometimes years. This pattern follows a remarkably consistent mathematical relationship first recognized more than a century ago. Immediately after a major earthquake, aftershocks occur rapidly. As time passes, they become progressively less frequent. Although the largest earthquake almost always arrives first, exceptions do occur. Occasionally, what appears to be a main shock later proves to have been merely a foreshock preceding an even larger rupture. That possibility explains why emergency managers treat every major earthquake with caution until the sequence becomes clearer. For residents along Mexico's Pacific coast, that caution remains entirely justified. Many structures weakened during the initial shaking may become increasingly vulnerable during subsequent aftershocks. Slopes destabilized by the first earthquake can fail without warning days later. Roads already fractured may deteriorate further. Coastal infrastructure must also be inspected carefully because repeated shaking can reveal hidden structural weaknesses that escaped immediate detection. Offshore, scientists also continue evaluating the rupture itself. Reverse faulting earthquakes possess the potential to displace the seafloor vertically, making tsunami assessment an essential component of every response. Fortunately, not every thrust earthquake generates a destructive tsunami. The amount depends upon several interacting factors, including the length of the rupture, the amount of vertical displacement, the speed of fault movement, and whether the rupture reaches close enough to the seafloor to lift significant volumes of water. Historical experience illustrates why these evaluations are taken so seriously. The nearby magnitude 8.2 earthquake during 2017 generated a damaging regional tsunami in addition to violent ground shaking. Although considerably larger than the present event, it served as a reminder that the Middle America Trench is fully capable of producing hazards extending well beyond the immediate epicentral area.